Yeah, so it's a pleasure being here. I think I gave a talk for the same series back in 2018 or something like that. So it's a pleasure to be back, and fortunately, I'll be not telling you about the same thing. Okay. So this talk is going to be on a series of works that we have done probably since 2018 on this field of 2D magnetism. Okay. So before I tell you about that, I should say that my group, we exclusively work on 2D materials. So here I'm just showing you a sampling of the universe of 2D materials out there. Unlike things like graphene and these transition metal dichalcogenides, which you probably heard of, we're more interested in layered materials that host some type of, let's say, more exotic ground state ordering, like superconductivity, density waves, magnetism. Okay. And over the years, we've done some work in various materials, but for the interest of time, I want to focus on some studies, in particular on this material, chromium triiodide, as well as some other things in that family. Okay, and maybe very briefly, I'll show you a slide on alpha ruthenium chloride, because I think it connects with some of the stuff here. Okay, so this field started for us back in 2017, where two works came out basically the same time, where they discovered magnetism, ordered spin states, okay, persisting down to the atomically thin limit. Okay, so this group at Berkeley, they looked at this compound chromium germanium telluride, and they exfoliated it down to, I think, 2 layers. And then they measured something called the Kerr rotation, which is an optical measurement of the out-of-plane magnetization of the sample. And they found that above a certain Curie temperature, you see an onset of this ferromagnetic state, and you see that it persists down to bilayer, even though there's some decrease in that critical temperature. This is not the system that we're going to be focused on. We're going to be focused on this system called chromium triiodide, which was isolated by a group at the University of Washington. And there they similarly exfoliated this 2D material, but they did a slightly different measurement. They looked at also Kerr rotation, which is the out-of-plane magnetization in the sample. And instead of measuring as a function of temperature, they just cooled it down, and then they applied an out-of-plane magnetic field. Okay. And so for the monolayer, what you can see is that essentially you see a nice clean hysteresis loop, which is indicative of the spin state in this monolayer, right? So they're up or down, and it's a classic ferromagnetic hysteresis loop. And this shows that you can have basically a single layer magnet, right? And so I think at the time, you can ask, well, why is this so interesting, right? If I know that the bulk material is composed of layers that each are magnetic, of course, if I strip it down to a single layer, right, it should still retain its magnetism, right? So I think at the time, this interest was looked upon through the lens of this famous theorem in solid-state physics called the Merman-Wagner theorem, right, where Merman, Wagner at Cornell proved under a very narrow set of conditions, okay, that it may not be possible to have any type of long-range order in low dimensions at finite temperature. Okay. Now, I say that this is under very strict conditions because they assumed, first of all, short-range interactions. So it turns out, okay, if you include dipole-dipole interactions, which are long-range, then you can kind of circumvent this theorem. Okay. Also, they kind of looked at this in the limit of infinitely sized sample. Okay, so if you look at finite size effects, it turns out that you can also stabilize magnetism in purely 2 dimensions. Okay, and finally, they assumed that the spin-spin interaction was purely isotropic. So there's no preferred direction in space that the spins want to point. And it turns out that there's generally always some type of anisotropy present in the system, and any type of anisotropy can essentially also circumvent this theorem. Okay, and that's something that which I'll actually be addressing in a quantitative way. Okay. So I at least want to point out those caveats why this might be kind of idealistic to apply, but nonetheless, this was, I think, part of the enthusiasm, right, from the community. So for me, I would say that the more interesting result from this group is the result from a bilayer. Okay, so this material, chromium triiodide, at least in bulk form, has been around for quite some time. And what was known about this crystal was that essentially all the interactions are ferromagnetic. So within the plane, all the spins are ferromagnetic. They're pointing in the same direction. And also the coupling between the layers are ferromagnetic. Okay, so all the spins are pointing in the same direction. But when they looked at a bilayer sample, they found that in the limit of zero magnetic field, so the ground state, there is no net magnetization in that sample, right? And they had to apply a finite field to polarize the spins. And so they assigned this magnetization state, okay, the ground state, to be a layer antiferromagnet. So there are moments, but they just cancel out, right, in two layers. Again, this was surprising because that is not what's established for the bulk crystal. Okay, and I'll talk about why this is the case later on, right? So our group, when we saw these results, we were very interested. But we are so before I should say that, I should say this is essentially the summary, okay, of what happens in chromium triiodide when you go from bulk to thin. Okay, it goes from a bulk ferromagnet to a layer antiferromagnet. And let's just accept this as some empirical result, okay, for now. So when we saw this, we were very interested, but we are mostly device transport people, and so we thought, could we try to utilize this material in some sort of device, right? But the thing is, this material is very insulating, so you can't just pattern or put down leads, okay, and expect to measure current in some arbitrary geometry, because when you cool down, the system's going to become insulating very quickly, okay? However, right, as long as we can make this material thin, then we can always tunnel electrons through it, right? We can use it as a tunnel barrier. And so that's exactly what my postdoc did. He used graphene, okay, on the bottom, graphene on the top, and then he used another material, hexagonal boron nitride, which is an insulator, just to encapsulate and protect everything, okay? But the basic geometry, and this is the same geometry that I'm going to be using for essentially the rest of the talk, is you have some metal, magnetic insulator, metal, tunnel junction, okay? Okay, so this is the device geometry, and then here's an optical image. If you look at it from the top view, essentially you have this thin region of chromium triiodide and sandwiched between graphene on top and graphene on the bottom. So when we measured the tunneling resistance for this device at low temperatures in the magnetic state, and then we applied a magnetic field, so we're looking at the tunneling magnetoresistance, it turns out that that resistance is also sensitive to the magnetic state of the chromium triiodide. Okay, so in the ground state, which is a layer antiferromagnet, I get a relatively large tunneling resistance. And then when I polarize the spins, the resistance drops, tens of percent. Right? And so this is telling us that in addition to magneto-optics, we can also use a device like this to read out the magnetic state of our material. And before I tell you the reason for this effect, we can say that, okay, so if I have two layers and then I get something about, I don't know, 20, 30% change in the resistance, okay, so that's not insignificant, but that's not huge either, right? So what if I have, let's say, a few of these layers, I don't know, 10 layers, 20 layers, and it turns out that this resistance change, it kind of builds up, okay? So here I have, I parked, so basically I'm looking at current through my device, so the conductance, and I parked at some voltage that I biased across this junction. And at low temperatures, you can see when I apply a magnetic field, I don't see just a single jump. Okay, I see many of these jumps. Okay, but the overall change in the current is about 4 orders of magnitude. Okay, so that's when I apply a magnetic field perpendicular to the layers. If I apply a field parallel to the layers, I see a qualitatively different change. Okay, so the current increases continuously, but then eventually it will also saturate here. So the overall change in the magnetoresistance is actually quite large. Okay, and so for people that look at large magnetoresistance materials, they always like to talk in terms of percentages, maybe to make their numbers seem even larger. So 4 order of magnitude change in the conductance is about 1,000,000% change in the magnetoresistance. And that actually is quite substantial. And so if I try to compare with other relatively large negative magnetoresistance effects, like, for example, giant magnetoresistance, that's about 100%. And then colossal magnetoresistance is on the order of about 1,000,000%. So at least quantitatively, it's similar. But there's a very important caveat that I'll mention later on. Okay. All right. So now let me get back to why we see this effect. Okay. So what we're kind of saying empirically is that the ground state, where the spins are anti-parallel for the different layers, that corresponds to a state of high tunneling resistance. And then when we apply a magnetic field and we start flipping these layers one by one, right, eventually we're going to polarize all the spins in the layers, and we're saying that corresponds to a state of low tunneling resistance, right? So why is this the case, right? So normally, right, when we have an insulating barrier that we tunnel electrons across, I think, right, we probably all, well, there's no pen here, right? We all know this standard picture of this, uniform barrier that we have to tunnel through, right? The electrons tunnel through. In this case, because the tunneling barrier is itself magnetic, okay, so that barrier height is actually spin dependent. So if we look at the calculations for chromium triiodide, if I look up into the conduction band, right, the first set of bands that appear are spin polarized up, right? And then I go up further in energy, and then I see the spin polarized down bands, right? So the bands are itself spin split. And so what that means is that if I look at the tunneling barrier, okay, for this state, it's spin dependent, okay? So the very first layer, spin up, has relatively low energy compared with spin down, right? But then when I go into the next layer, it flips, right? So now spin down has low energy and spin up has high energy, right? So I get this zigzag sort of, tunneling barrier, which you can imagine overall, that's still a relatively large tunneling barrier, right? But then if I look at the tunneling barrier for this state, now it looks like this, right? So the effective barrier, at least for one of those electron spin species, right, spin up, has been lowered, right? And so a small change in that tunneling barrier, even if it's just for half of the electron species, that corresponds to a large change in the conductance, right? And so that is exactly the effect that is causing this large tunneling magnetoresistance. Okay, we can see this more clearly if we were to look at the current voltage characteristics of our device as a function of the magnetic field, right? So you see that this thing is nonlinear, okay, because it's a tunneling device, right? That is, it's a nonlinear device, so you would expect it to be nonlinear. But then, the point at which this current turns on, that's kind of indicative of this gap, right? Of this activation of this barrier. And so when I increase the magnetic field, you see this curve just shifts over to the left. And so that barrier has decreased, right? And so here's the caveat that I was telling you about, right? So it turns out, right, if I apply a critical, let's say, voltage right here, and then I dial up the magnetic field, the current is going to increase exponentially, right? As you can see, and that's how we get our 1,000,000% change in the resistance. However, if I current bias my device instead of voltage biasing, right, then you see that the change in the voltage is not going to be nearly as much. And that's just a manifestation of the fact that this is a nonlinear device, right? So CMR is a linear response effect, right? So that's an important difference. Okay. Now, from these curves, if you're familiar with these scaling relations with current and voltage, you can actually try to extract all these different barriers. Okay, so in the ground state, I can get this effective gap for the AFM state. I can apply a magnetic field and extract this ferromagnetic gap. I can raise the temperature and then get this gap in the normal state. I can extract all those things, but I don't want to plot that for you because in a way, those numbers aren't so fundamental because they're always referenced relative to the graphene Fermi energy, right? And that could change depending on the doping. The more fundamental quantity is if I take the differences between those numbers and I get this exchange splitting in the chromium triiodide between the spin up band and the spin down band. Okay, so that's what we can extract. That's meaningful from these current voltage measurements. And you see this gap is relatively large, 130 millieV, okay, at low temperatures. And then as I hit the Curie temperature or Néel temperature, whatever you want to call it, okay, at around 40, 45 Kelvin or so, then that gap closes and goes to zero, right? So we only see this effect in the magnetic state. Okay, that's what that means. So why is it that when we apply an in-plane field, right, the current or conductance changes continuously? Well, when we apply an in-plane field, then we're not flipping the layers one at a time. Essentially, the spins are just all slowly canting, right, until they become fully polarized in plane. However, this picture that I've shown you here, right, we don't care about the absolute directions of the spins. We only care about their relative direction, right, because that's what determines these barriers. And so this state where all the spins are pointing in plane has a similarly low resistance as this state where the spins are all pointing out of plane. Okay, it's just the way the evolution with the magnetic field is different. Okay, good. So are there any questions on that part? Yeah, feel free to ask. Okay. All right. So I want to move on to the next part. So great. So using this TMR measurement, it turns out that it's a very sensitive probe of this, effectively this interlayer magnetic coupling of these materials, right? And this is essentially a ground state effect. Okay, so we would like to do maybe go one step beyond that. We want to try to extract some sort of at least minimal spin Hamiltonian for 2D chromium triiodide. Okay, and so the simplest Hamiltonian that we can think of is probably the Heisenberg Hamiltonian, right, which is the one used in the Merman-Wagner theorem. And so the spin interactions are isotropic, and so there's just a single exchange term, right? That's the same between x, y, and z. But we know that this cannot properly describe the chromium triiodide because, as I told you, right, the spins preferentially like to point out of plane. And so that means there's some anisotropy that is actually making them point that way, right? And so to model this, right, what we can do is simply add an exchange anisotropy. Okay, so the exchange on the z term, we're going to say, is different than on the x and y. Okay, and if alpha is larger than 1, then the spins preferentially want to point out of plane, right? So we would like to at least extract these parameters in this minimal spin Hamiltonian. And you can ask, okay, so how is it that we can try to do that, right? So one of the ways is to try to measure the magnon dispersion. Okay, so we measure the excitations of this magnet, which are magnons or spin waves. And they actually have some interesting dispersion relation, right? And you can see that actually this is relatively straightforward to calculate because it's just a hexagonal lattice. And if you know anything about graphene, this looks pretty much exactly like with the dispersion, the electronic dispersion for graphene, right? You even have like a crossing at the K points here, right? Okay, so if I can measure the magnons, the excitations at certain critical points in this Brillouin zone, then, so for instance, at the gamma point, okay, which I've schematically shown here, okay, so gamma, this one, that's when both sublattices are rotating together, okay, and up here, that optical mode is when the two sublattices are rotating out of phase, okay, so that's at least a nice visual for the spin waves at the gamma point. So if I can obtain the energies at the gamma point, right, then unsurprisingly, they depend on parameters J and alpha, and then at the endpoints as well, right? Then if I can measure these energies, then in principle, I can back out what J and alpha are, right? So at McMaster, I'm sure that everyone is familiar with neutron scattering, right? That's probably the best way for you to try to measure the dispersion relation for the magnons, right? But the problem is that can only work for bulk crystals, right? And as far as I know, actually pretty large bulk crystals. So if we have just a layer or two, that's not going to work, right? There's also Raman scattering, right? But those typically can access only the magnons at the gamma point, right? You're limited essentially by the light cone of the photon, right? Which could be fine, right? But I want to tell you about a different technique that we can use to also detect magnons in small samples that's not limited at the gamma point. So before I do that, I just want to quickly point out, if alpha here is 1, so in the limit of the pure Heisenberg model, right, you have this acoustic mode drop down to 0 energy. Okay, so the magnons become gapless, right? So this is why you have the Merman-Wagner theorem, because at any finite temperature, then I can excite magnons. And in 2D, it turns out that those fluctuations are strong enough to wash out any long-range order, right? As soon as I introduce some anisotropy, then I start to produce a gap, right, at the gamma point. And so I lift up that Goldstone mode. And then at some low enough temperature, I can stabilize the magnetic order because there are no magnons to wash it out, right? So that's at least the rationale, okay, behind that theory. Yeah.
But the ferromagnetic theorem also applies to XY system, right?
Yes, I think so. Yeah.
And an XY system would also not have a gap.
That's right. So if alpha is less than 1, I think it still remains gapless. Yeah. Okay. Right. Okay. All right. So what is this technique that I want to tell you about? So it relies on that same tunneling geometry. Okay? It's a technique called inelastic tunneling. And the way that this works is the following. So if here I've just drawn a simple tunnel barrier for chromium triiodide, I've ignored the difference in the different spins, okay? So that up, down, spin stuff, it's not really relevant here. So I'm just going to represent this as a smooth barrier, okay? So when I apply a very small bias across my electrodes, then I know that electrons are going to tunnel from the source to the drain. And they're going to tunnel elastically, meaning that no energy is going to be lost during the tunneling process itself, okay? Eventually, the electron is going to relax down, right, in energy at the drain, right? But the tunneling itself is going to be elastic. Now, let's say I increase my bias, right? Then at some point, my voltage is going to surpass the energy of an inelastic excitation inside the insulator, like a magnon or phonon if it's a magnetic, like a phonon or magnon if it's a magnetic insulator, right? And when that happens, essentially the electron can create a magnon or phonon, reduce its energy, and then tunnel across inelastically, right? So this essentially opens up another conduction pathway, right, for electron tunneling, an inelastic tunneling pathway on top of the elastic channel. So I would expect when I reach one of these modes to have a slight increase in my tunneling conductance, right? So if I were to look at the local tunneling conductance, let's say dIdV, as a function of the voltage that I apply, when I reach these critical energies, I'm going to get a little kink in my conductance, okay, because of this extra conduction channel. Okay, and these kinks are exactly the energies, right, of these magnons. And so to see that more clearly, I can take the derivative of this curve. So the kinks become peaks. And then I can just read off the peaks as the energies of my magnons or phonon, right? So in this case, I see 4 peaks, but really it's symmetric between positive and negative bias. And so there are 2 peaks, right? So one at 7 millieV and one at 15 millieV. But this alone does not tell you whether it's a phonon or magnon, right? So to distinguish them, we can apply magnetic field, right? Because phonons probably won't disperse with magnetic field, and if it's a magnon, it would disperse like the Zeeman shift, right? Okay, so this is that same spectra. Here I'm just showing you in a color plot so you can see it. If I apply a magnetic field along the easy axis, the c-axis, you can see actually these features shift, and the slope of this shift gives you roughly a g factor of 2. So it's what you expect for a magnon, right? But as I said, we are not necessarily just sensitive to the magnons at the gamma point, right? That's only the case for Raman spectroscopy. So where are these magnons coming from, right? So here's where we actually have to make an educated guess. So in principle, right, we are sensitive to magnons across this entire spectrum, right? And so then you have to ask yourself, well, where's the density of states the highest for the magnon, right? That's where they would most likely be coming from. And if you know something about graphene, you would know that there's a Van Hove singularity at the M point for graphene, right? So the same thing is here. There's an extra density of states at the M point coming from this Van Hove singularity for the magnons. And also at the M point from this calculation, you can see that this energy is basically twice the energy of that lower branch, right? So that's something else that gives it away. Okay, so if we look at our data at zero field, that's pretty much the case, right? So we can model this, okay, with our spin wave calculations. Okay, this is the result from our spin wave calculations. If we look at the endpoint, and it's a pretty reasonable match, I would say, right? So from this, we can conclude that we are looking at the endpoint magnons, okay, from the chromium triiodide, and we fit it to the spin wave relation, then we can actually extract what J and alpha are. All right. So another thing that we can do is now we can apply a magnetic field along the in-plane direction. Okay, so this is the hard axis, if you will. And if you apply it along the in-plane direction, for the if we could measure that this gamma point mode, right, it would actually close and open up. Okay, but we can't measure this mode. For the M point, it would actually just be stiff and then to start to gradually increase. And that's pretty much what you see, although, the peak is pretty, relatively wide, right? So it's pretty stiff down here, and then it starts to open up above that anisotropy field. So, putting these things together, I think we're reasonably confident that these are magnons coming from the M point. Okay, so I'm going to show you those results that we extract in comparison with the spin waves. These are the J and the alpha that we can extract. In addition, I told you about that exchange gap splitting in the conduction band, 130 millieV or so. Okay, the interlayer coupling in thin chromium triiodide is AFM, and then this is the TCs, okay, going from thick to thin. So it doesn't really change at all. And there's something else I want to comment on this, but yeah. We don't think those are phonons. Yeah. I don't think there are phonons in that energy range.
There's always low energy.
But do they have a high density of states, right?
Well, I couldn't see where so what energy
Yeah.
range is that?
So this is between, up to 20 millieV or 15 millieV, let's say.
But
Yeah.
it must be known. Right?
Yeah,
I've
seen it, but I don't have, I'm not confident enough to tell you exactly what it is. I don't think, as far as I recall, there's any, singularity in the phonon dispersion in this energy range.
But I mean, there's always zone boundary acoustic phonons. It's just a question of where that is.
Okay. I don't have it off the top of my head. All right. Okay. So the important parameter that I want to tell you about. So this J parameter is reasonable if we compare with neutron scattering, but also this anisotropy, right? So this is about 4%. And I mentioned that this anisotropy is responsible, right, or at least has a role in stabilizing magnetism in 2 dimensions, right, because it gaps out your Goldstone modes, right? So actually a 4% anisotropy, from what I learned, is actually a relatively strong anisotropy in magnets. Okay, you can correct me if that's not the case, right? But regardless, if we look at this effect, right, so a 4% anisotropy, if we look at the TC, right, for this system going from thick to thin, there's basically no change, right? It's 1 degree change, right? We've done this measurement. Oh, sorry. Yes. From this, we can also extrapolate other things. Okay, I won't talk about this, but we've also done this measurement on another system, chromium bromide. Okay, I didn't show you those results because we don't have time, right? But basically, in addition to a smaller TC, which is reflected in smaller energies, the anisotropy is also a lot weaker. It's about 1%, right? And now you look at the evolution of the TC. So going from few layers, right, the TC is about 37 Kelvin, right? 2 layers, 36, and then down to monolayer, it drops by 10 degrees or so, right? So that's a relatively large jump, right, compared with chromium triiodide. And these are all finite size samples. We don't think this is because of dipolar interactions. So we think that just by decreasing that anisotropy, right, then that leads to that more dramatic change in the TC. And we think this is the same effect in that chromium germanium telluride system that I showed you earlier. All right, does that make sense, or any questions on? Yeah.
Your far right column. Are you saying that even with 2 layers, that the interlayer coupling is now ferromagnetic for the bromide?
This is always ferromagnetic. This is ferromagnetic. Yeah. Right. And I'll return to this issue of interlayer coupling very soon.
What's the magnets?
That is the splitting between the first conduction band, which is spin up, and then the next set of conduction bands that are spin down. Band structure calculation, yeah. So it's not. It's probably the same order of magnitude. It's not very close to the calculations, probably because this doesn't have any momentum information, right? It's just a single value. Yeah. But that's what we extract from our TMR measurement. All right, so before I move on to the second or the last part of my talk, I just wanted to quickly say that so when we had these results, we were pretty excited because we thought that there are not so many techniques out there that can measure magnons, right, in atomically thin systems, right, especially if it's far away from the gamma point, right, and so we knew in part from I think Pat's work many years ago, right, that ruthenium chloride was a very interesting material for Kataya physics, right, and if that doesn't mean anything to you, that's okay. But we wanted to basically do this same experiment to measure the magnons in the ruthenium chloride, okay? And so that Hamiltonian is much more complicated, right? So this is the Kataev term, and then there's some off-diagonal blah, 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 right? You can clearly see that this is more complicated, but you have smart theorists that can essentially calculate what the dispersion relation would look like for the magnon, okay? So I believe this was linear spin wave theory. This is exact diagonalization, which kind of, for the higher energy features, it kind of washes it out due to interactions and such. So I'm told by Steve and Roser that this is probably the more realistic one, right? And so you see clearly that there is a hot spot, right, for the magnons, not at the gamma point, right? The low energy magnons are coming at the M point or Y point at around 1 millieV. So if I were to do an inelastic tunneling measurement that is, let's say, sensitive to all of these magnons, then I can probably just integrate over the Brillouin zone, right? And so what I would expect to see is a low energy feature coming from these hotspots at around 1 millieV, and a broad continuum of features coming from these states up here. At least that is what the theorists have calculated, right? So from our measurements, okay, we've measured 3-layer ruthenium chloride, 2-layer, monolayer. In all cases, okay, so the vertical axis is temperature. So in all cases, right, we see a 1 millieV mode coming here, right? And then above the nail temperature, that feature goes away, right, as you would expect. But this continuum feature, right, actually persists up to higher temperatures. So we've only measured up to 10 or 12 Kelvin. But if these results are consistent with Raman and neutron studies, and from their studies, at least for the bulk, it goes up to even higher temperatures than that. Okay. So I just wanted to show this because I thought this was, maybe people here, something that people can appreciate. Okay. But I don't want to spend too much time on this because it probably requires a whole nother talk. So I wanted to get back to this issue of chromium triiodide, but I'm happy to take questions. Yeah. Very good. So we don't know, okay? And the reason is because for 3-layer, it's insulating enough that we can apply a larger voltage without zapping our device, right? So it gets way too noisy, so we don't know. Yeah, good question. All right. So am I okay on time? Yeah, okay. So when did we start? 2:30? Yeah, so I probably have about 15 minutes left or so. Yeah. So I wanted to get back to this issue of why is it that CRI, right, going from thick to thin has a change in this interlayer coupling, right? So the intralayer exchange is pretty straightforward, right? I think even by the good enough kind of Moiré rules, it's always ferromagnetic. Okay, but out of plane, it's actually more complicated, right? So the exchange has to go through 2 of these iodine ligands, right? So it's actually called a super exchange. So you can imagine that if there's a slight shift, right, between these 2 layers, then the exchange can be completely off, right? And it's also a much weaker exchange interaction compared with the in-plane exchange. And so from calculations by DFT, that's exactly what they see, right? So for certain stacking, like rhombohedral, the exchanges, interlayer exchange is ferromagnetic. But if they, look at another low energy stacking configuration, monoclinic, then it becomes antiferromagnetic. Okay, so what happens in bulk chromium triiodide is that at high temperatures, it is in this monoclinic stacking phase. So if we could cool down in this phase, then we would get an AFM interlayer coupling. But for the bulk crystal, there's actually a structural transition that brings the low temperature structure to the rhombohedral state, and so that coupling becomes ferromagnetic. Okay, so if you have any experience with 2D materials, you find that often these interlayer stacking transitions, they become quenched when you have in the limit of few layers. I don't know exactly why, maybe because of pinning or things like that, but thin CRI, it retains the monoclinic structure down to the lowest temperatures. Okay, and this structure would give you an AFM coupling. Okay, so that's the reason. Now you can say that, well, if this interlayer magnetic coupling is so sensitive on the stacking, what if we took two layers and then we just gave it a slight rotation, right? Well, then in principle, you would be able to realize all the different stacking configurations, right? Some regions would be monoclinic, some would be rhombohedral, and others, right? And what that means is you'll have regions where the coupling is ferromagnetic, like in green, and regions where the coupling is antiferromagnetic, right? So it's kind of, if this is true, this would be a nice way to engineer like magnetic textures, right? Which is relatively difficult to do when you try to grow crystals. Okay, so if this is the expectation, right, then you can say, well, what is the first measurement that we can do to try to confirm this? Well, probably the first measurement you can do is some sort of magneto-optical measurement, like Kerr rotation or magnetic circular dichroism, because what you would expect is not just to see a purely FM state or an AFM state, but you would see a mixture of both, right? Because the size of your laser spot is going to be much larger than this Moiré length scale of 5 or 10 nanometers, right? And so that's exactly what was done by, I think this was a group at Cornell, and then this was a group at University of Michigan. So this group, so both of them, they didn't use Kerr rotation, they used magnetic circular dichroism, but it measures the exact same thing, which is the out-of-plane magnetization in the sample. Okay, so for the monolayer, right, you see this nice hysteresis loop. And then if you remember for untwisted bilayer, you would see no loop, right? You would see basically two steps, right? And so in this twisted bilayer system, they kind of see a mixture of those two, right? You can kind of see two steps, and then on top of that, you see a little loop, right? So the claim here is that you see coexisting AFM and FM order. And then this was done by my colleague in Michigan on a 4-layer sample. So 2 bilayers that are slightly twisted, but it's effectively the same thing, right? So you, instead of seeing a pure step or 2 steps, you see a little hysteresis loop inside. Okay, so I would say this is the first signatures of coexisting AFM and FM order. Okay, but it turns out that this is not the whole story, and so I want to show you some of our recent results using the same geometry, okay, tunneling magnetoresistance to probe the magnetic order in these systems. Okay, so the system that we were looking at, so we were also inspired to look at this twisted bilayer, so 4 layers that are twisted, for reasons which I can get into later if you're interested. But yeah, so basically the sample would look like this, right? So you have, this is the natural bilayer, so this would be antiferromagnetic coupling, this would be antiferromagnetic coupling, and then in the middle where you have this twist, then you basically realize all these different couplings, right? And so you can try to ask yourself, maybe if we can try to anticipate exactly what would happen, right? So at the end of the day, what I'll just tell you is this: there's no way that you can satisfy all the interactions at the same time simultaneously, right? Because for the twisted layers, right, you're going to have some regions, most of the time it's going to want to be spin parallel, as I've shown in red, but every now and then it's going to want to be spin anti-parallel, right? But the outer layers that are not twisted always want to be spin anti-parallel. So you can't realize that all the time unless you form some domains, right? So here, this is an example of a potential domain that we've formed, right? And so here, right, essentially we've sacrificed some coupling between these two layers. So it wants to be spin anti-parallel, but we forced it to be parallel. So this costs some energy. Okay. But there might be another way that you can form these domains. So here, inside these bubbles, right, the spins want to be anti-parallel, but they don't necessarily need to point in the out of plane direction, right? So here I made them essentially fully in plane. Okay, so that also minimizes the AFM coupling energy. But then there's a neutral interaction, right, between these layers and these layers, right? And just so schematically, right, you can kind of see that how these energies are basically they balance out, right? So actually, these are both energetically favorable states if you do the full calculation, right? But you notice that these states, if you look at it carefully enough, they're going to have the exact same net magnetization, right? So that means something like MCD or co-rotation would not be able to distinguish between these types of domains. But my claim is that the tunneling magnetoresistance measurements will. Okay, so this is the device geometry that we fabricated. So this is the 4-layer structure that I showed you before. We have graphene as our electrodes, and then we have boron nitride that encapsulates the sample. And so we can apply a voltage on one of the graphene electrodes and measure current, okay, just like what we always do. But on top of that, we can also put a laser, okay, and then we can scan that laser across the sample. And this laser allows us to measure the photocurrent in our device, okay? So if we apply a small voltage, okay, that light would induce some current. And so why we want to do that, I will show you right now after this. But basically, we can scan the laser across the sample and measure the photocurrent. Okay, and as a sanity check, we can confirm that it's coming right at the junction where we expect it to. Okay, so it's localized in our device tunnel junction. And so the reason why we want to do this is that because we can also measure this out of plane magnetization in our device using this geometry. Okay, so magnetic circular dichroism is basically the difference in absorption between left and right hand circular polarized light. I don't know why. Okay, magnetic circular dichroism is the difference between absorption in the left and right circular polarized channels. I can do the same thing in photocurrent because in order for the device to generate photocurrent, it has to absorb some of that light, right? And so you can see that this hysteresis loop that what we get from our photocurrent measurement is very similar to what was seen before, right? And then on top of that, we can measure it for the 4-layer. And there is no hysteresis, right? So you just see these steps. So this is the naturally untwisted 4-layer, okay? So now that we know that our devices at least have this Moiré structure that is consistent with previous results, let me go on. Okay, so it turns out that this system is complicated enough where we actually need to do some simulations of the domain dynamics to figure things out. Okay, so what's going to go in our simulations is the monolayer Hamiltonian with the J and the alpha that we extracted earlier and that just presented. Okay, but now we have 4 of them. Okay, and then we have 4 layers, right? So 2 of them are untwisted, so it's just going to give the natural AFM interlayer coupling, so that's a constant. But then the middle 2 layers, that is going to have a spatially dependent exchange coupling, which I mapped out earlier for you. Right? So we're going to put that all in there and our Zeeman interaction. And we can actually try to simulate what the magnetization would look like as a function of the out of plane magnetic field. Okay, and so, you know, qualitatively, I would say this is similar to what we actually see in the experiment. Right? So the size of the loop kind of depends on adjustments in the parameters, but overall it's there. And and beyond this, what we can do is we can, at these certain points, right, we can actually plot out what the full spin structure would look like, at least at the simulation level, okay? So there's a lot of stuff going on. You don't need to look at all of them because it's going to take forever, but at least we can look at what's happening around zero field. So this is the ground state, okay? So these domains are forming at basically those Moiré locations that want to have, let's say, the different couplings, okay? But it's basically this sort of schematic that I showed you earlier. Okay, so when I apply an out-of-plane magnetic field, it seems like the sample wants to nucleate these out-of-plane, what I call out-of-plane domains. Okay. However, we can also measure now the tunneling magnetoresistance, right? And in TMR, we can apply magnetic field in any direction, right? As I showed you before. So when I apply magnetic field out of plane, right, we have this orange and then green curve. So there's some hysteresis between how we sweep the field, okay? But the resistance at zero field is the same, right? There's a singular value, right? But when we apply an in-plane magnetic field, we see that there's a different resistance at zero field, right? So remember, this is all taken at zero field, so that means the ground state spin texture is changing. If they were the same, we would have the same resistance, right? So the fact that we see a different ground state TMR is telling us that we see different types of ground state spin configuration. Okay, so right, so if I compare this with the untwisted four-layer, right, essentially within the noise, there's just a single value, right? So there's only basically a single ground state. So what is causing this difference in the ground state? Well, I already alluded to you that it's the different spin configuration. Okay, so again, we have to turn to our simulations. So what I'm plotting here, so in addition to the outer plane spin component, I'm also showing you the in-plane spin components, x, sy, and x, sx, and sy. Okay, so we still have these domains, and then they actually form some type of interesting nodal structure in plane, which is saying that at the simulation level, this is some type of skyrmion, right? So now what we're going to do is we're going to take this ground state structure that we established, we're going to apply an in-plane magnetic field, and then we're going to remove the in-plane magnetic field, right? Because what I said, I'm showing you, it's all ground state stuff. Okay, so I'm going to apply an in-plane magnetic field, and I'm going to remove it, and now you see that the spins have gone into some different structure, right? In fact, they've gone to this sort of structure. So now these domains have become polarized in plane, and they're pointing in opposite directions in these bubbles between these two layers. Okay. So this is what it says from the simulations. On top of this, what we can do is we can take these simulations, we can calculate what the TMR we would expect, and it turns out that this one, okay, has a higher tunneling magnetoresistance than this one. Okay, so that's actually consistent with our results. So the story is, at the end of the day, there's not just one ground state for these Moiré twisted Moiré spins, right? Depending on how we apply the magnetic field, different domains would tend to nucleate. When we apply an out-of-plane magnetic field, we tend to stabilize these out-of-plane domains or skyrmions, and when we apply an in-plane field, we tend to stabilize these in-plane domains. Okay, so this is what we get from our experiment. All right, so that's pretty much it. If there are no other questions, at least I want to acknowledge the people that did the real work. So the earlier stuff on the TMR, on the chromium triiodide, was done by my former postdoc, Hyung-ho Kim, who's faculty in Korea now. The ruthenium chloride and the twisted CRI work was done mostly by my student, Bowen, okay, I guess, who's found a cushy quantum computing job. And then the simulations, the magnetic domain simulations, were done by my colleague Junichi Okamoto. On top of that, we had a lot of support from various people. I would want to point out that the crystals were grown by a collaborator in Lei Hechang in Renmin University in China. Well, okay, it's all here. Yeah. So thank you.
So thank you very much, Adam. We have time for some questions.
So n is equal to the number of chromium triiodide monolayers. At what n do you reach the bulk behavior?
Yeah.
Presumably that's the n at which the monohedral interlayer.
Yeah, that's a very good question. We can't tell you that from our measurements, because in a tunneling measurement, we cannot measure a crystal that's infinitely thick, right? Yeah. So my colleagues, my colleague Liu Yanzhao from Michigan, so they actually measured using Raman, right, the bulk crystal, and I think what they found is that there are surface layers even on the bulk crystal that is anti-ferromagnetically coupled, and the bulk is ferromagnetically coupled. So it might always just be some surface thing, but yeah. What was that? No, this is a company in Toronto. Oh. Okay. Okay. Oh, yes. Okay, I get it. Yes. He was very productive. Yeah.
So, you showed these the twists at 1 degree.
Yeah.
So have you looked at other twists, and is 1 degree easier than others?
Yeah, so we actually had to do a whole twist dependence because that's what the reviewers asked for. Basically, 1 degree is where these coexist. If you go, I mean, obviously nothing interesting happens at 0 degrees in terms of this, right? When you go to high enough angles, you also stabilize one domain. So the reason why one might be stabilized over the other is you can see that for this one, right? If you draw some cross section here, the spins have to turn 180 degrees, right? Whereas here, they only have to turn 90 degrees and they turn back up. So depending on that Moiré length scale, if you really shrink it, this is going to be more favorable, right? Because they don't have to turn a full 180 degrees. And so there's only one state that we see at larger twist angles, and we think it's this state. However, when you go to, I'm still talking about a few degrees, right? Because once you go to much larger than that, then the Moiré length scale becomes meaningless, right? So a few degrees is usually where things happen.
Go ahead, Bruce.
Well, I was just going to ask if this method of measuring the spin wave density of states has been applied to well, I guess you already told that it was applied to chloride.
Yeah.
And is there an energy scale over which it works well, or could you use this for the Coop rays? The energy scale for the spin waves is much higher.
Good question. So no, because so we're ultimately limited by the voltage that we apply, right?
Yeah.
So that is the energy scale. Now there are technical, issues with applying a very large voltage on a very thin sample, right? So I would say there's no fundamental, but I would say there is a low energy scale, right? And that is limited by the width of these peaks. And so right now, 1 milli eV, that's probably the lowest we can go, right? So that's exactly why we can't access the gamma point, because that's at much lower energies. We need to do something else.
Yeah, John?
So you said that the tribromide is always ferromagnetic.
It's always ferromagnetic, yeah,
So
I think, yeah.
So the difference between the iodide and the bromide is interlayer distance.
And the stacking. So I don't remember the stacking. My guess is it's always one of those. Yeah. Yeah. Yeah.
So putting the iodide in instead of bromide increases the interlayer separation enough that other kinds of stacking.
That's my guess, but that's about it. Yeah. I think at the end of the day, you just do the DFT calculation. You see what the differences in these energies are. Right?
Well, if there are no other questions for Adam, maybe you can join me in thanking him for an excellent talk.
Okay, thank you very much.